In the Merton model, the number of jumps follows a Poisson process. The jumps are multiplicative, which is a natural choice when the diffusive part is geometric Brownian motion. Robert Merton introduced jumps to model idiosyncratic shocks that would affect only the individual asset and not the market as a whole. The expression for the stochastic differential equation of the Merton jump-diffusion process is geometric Brownian motion supplemented with a jump term. So the drift term is simply proportional to the level of the process. The diffusion term is also proportional to the level of the process. And finally, the jump term has also the same form. The differential equation is supplemented by the initial condition S of t0 is equal to S0, where t0 is the first time at which the trajectory is going to be monitored. The jump process is defined in terms of a sequence of random arrival times. The first jump arrives at time tau1, second jump at times tau2, and so on. So j of t is equal to the sum from j equal 1 to n of t, and we're going to write the size of the jump in a different way. We're going to write it as yj minus 1, and this will be convenient for this particular form of stochastic differential equation. Yj in the Merton model is sampled from a log normal distribution, but it could be sampled from some other positive distribution. The counting process is written in terms of the indicator function, whose value is 1 when t is larger than tau j, and 0 otherwise. Let's integrate the stochastic differential equation in an interval without jumps, and then in an interval with a jump. So first we have the interval TITF without jumps. And now the size of this integral can be arbitrary. The value of the process at the end of the interval can be expressed in terms of the value of the process at the beginning of the interval using the formula for geometric Brownian motion. X sub f is sampled from a normal 0,1 distribution. Let's now integrate the trajectory in an interval around jump j. The value of the trajectory right after the jth jump can be expressed in terms of the value of the trajectory right before that jump times the size of the jump. Again, in the Merton model, the size of the jump is sampled from a log normal distribution. So we see that the jumps here in this model are multiplicative. Let's simulate a trajectory from the Merton jump diffusion process. Remember that the trajectory that starts at 100 follows the diffusion process until it encounters the time for the first jump. Then we generate the size of the jump, and from then on the process will follow diffusion. Another jump, diffusion, another jump, etc. until we simulate for the whole length of the interval. If we simulate other trajectories, we'll find jumps at other times and of different sizes. This is, for instance, a simulation of 5 different trajectories from this model.